Swayam Prabha. Digital India. Educated India.
Now we have just have come to a point, okay, that to correlate the correlation between the NMR, the magnetic measurements, and then the EPR, and they are going side by side, parallel. We are seeing where they are same, where they are difference, and what pictures we can probe in NMR, EPR, what we can probe in magnetic measurement, okay, and some similarities with the NMR. Okay, now so now we are going to the suppose the what we probe about EPR. So what's your name? Who asked me about you at the corner? Mohanlal. I hope he's not the same Mohanlal who makes a lot of movies. 2 N1 I1, okay, plus 1 if you have one nucleus, 2 Ni plus 1, 2 Ni plus 1. This is the only to count the number of hyperfine lines, okay, depending upon the spin of the nucleus. So if the nucleus spin actually half, you get 2 signals, okay, like this. And if you have one no spin active nucleus, you will get 1 signal. If you have two spin is 1, then get 3 signals. They are very pretty simple. You just put it here. Okay. Now point is that EPR spectroscopy is just about number of lines it produced. Okay. It probes about the coordination environment. Okay. So how the ligands are coming or bonds are formed, what is the coordination number or how many bonds are formed, and distribution of the electron density around the nucleus. It is the spread it speaks about that. The line try to remember that. So EPR spectroscopy speaks about the spin density distribution and the nature of coupling and how much deformation, everything it can speak. Now you will say how. So that's the point I told you. You take a balloon and then try to squeeze any way you want to deform the shape. Every time you squeeze, at some point stop and take a picture. Another you keep on doing, ask some guys to take picture, and you see what are the shapes you are making without knowing. When you make the compounds of the metal complexes or somewhere else or in the organic radicals, you see the distribution of the spin densities are very different. Okay, and you can have many ways of keeping the spin densities of the same spin. Suppose if I have a methane molecule, okay, this is a methane molecule, and then I make a CH3 dot, and if it is a like in the p orbital is like this, okay, I can have the same one electron in the benzene ring. I can make dot minus 2, or I can put in this molecule and then dot minus, okay, and I can take different type of molecules. I can keep the same one electron in different way. Do you think the spin distribution of density here, shape, and the spin density here and here are the same? No, it's changing, right? So that effect also you will see in the EPR. So now if I keep one electron in octahedral complex, tetrahedral complex, square planar complex, or square bipyramidal complex, they will be same? No, EPR will change, their shape will change. Signal will be there, okay, but shape will change. Okay. Now that is what also we can prove. Now these lines you see here, these are the coupling constant. So by this separation, you can also speak about their how strong they are coupled. If I get the same line, 2 lines, 3 lines, okay, but this time they are like this, they are coming. Okay, now you see separation is higher. Here you can separation is smaller. So what does it mean? So that means that the electron is In the second case, orange case, more strongly coupled than the first case. Okay. And if I get the same spectra, not like this, spectra becomes like this. What does it mean? So they will speak about the distribution of the spin density now. So here they are similar shape, and then you cannot speak much about the distribution here. Or moment this shape changes to like this, you have a different thing to say. Okay. Okay. So now I am giving you the what you call it, a concept that, okay, so you take a spherical sphere, this is a sphere, okay, and you have the sphere means that distribution of the electron density around the nucleus is spherical. So if you take a center, if you go any direction x, y and z direction, all direction the average spin density is always same. So I will call it spherical and isotropic. Okay. Okay, and in each case I can have a g component x, gy and gz. Okay, all will be the same. Okay, same value. Now if I same electron density, the electron density, if I make bonds in a way, okay, and their ligands are in a way that their distribution is not spherical, it has a change to a shape like this, okay, or change a shape like this, okay, or it changes shape like this, it has meaning, different meaning. Now how does it matter to you? Because this will be reflected, their shape will reflect in the EPR spectrum. Okay. So in this case, this is a g will overall g is equal to root over gx square by gy square and gz square by 3. Okay. So if all are same and you see these 3 will cancel and then you get equal to g. But if they are different and then you still get a average g, but the shape will come different. Okay. Now, Abni, can you call Subuhan? I will be needing now some slide. Okay. Not now. It will be 5 minutes later. Ask him to come with the slides with the in a pen drive. Pen drive is okay. Huh? Okay. Fine. So now you try to see that this is actually spherical shape and this is actually kind of a non-spherical, and we can call it, if they are x, so now I am getting a condition gx y equal to gy but not equal to gz. Okay. So if this is the z axis and this is x and y, they may be the same but this is different. If z is different, it will be elongated that direction. That means that electron density along z axis is much higher than the x and y. If I get this one, that means x and y are higher than the z. Okay. So this is a, both will be called axial type, but it's this is a case where gz is greater than gx and gy. Okay. In here gx and gy, they are maybe the same or greater than gz, and this is the case where gx, gy and gz are not each other. This you can see in the EPR spectroscopy. Okay. So now a system is symmetrical, a compound electron spin density is symmetrical or unsymmetrical distribution and all, you can probe by EPR spectroscopy. So I don't, I think this is something very very crucial parameter. And why it is important? Okay, we have studied about bioinorganic complexes, metal complexes, copper complexes, electron transfer catalyst in copper complexes with tetrahedral then this dicopper systems and all, right. Now copper system is the one where you have a tetrahedral, distorted tetrahedral, square planar, okay, all kind of geometry, and then based on the geometry, these shapes are coming different and the coupling constant will be different, okay. So now if you go to copper ion, now let me go to the copper ions, okay. So if I have a copper ion and his copper ion has a always it is a little bit distorted. This distorted means that because of the Yandra distortion, okay, that it cannot make always all bonds same. It is always distorted geometry. So and then copper one has 63 and 65. These are the isotopes, and all the time their spin both are for the spin is 3/2. So now if we apply this formula 2Ni plus 1, so for 1 copper you get 2 into 1 copper, I equal to 3/2 plus 1, if you cancel out you get 4 signal, okay. So you are supposed to get 4 signals like this, okay. Now in EPR spectroscopy you should not keep changing this, you have to count from the either from this, either from this, okay. Now you see here 1 2 3 4, and here we have 1 2, something is wrong, yes, so we have to, okay, now it's fine. So now you see these are the 4 signal, and where is the center, so you have to go peak to peak this side, peak to peak this side, so somewhere middle here is the center, okay. So this side 2 and this side 2 and here is the center. So locating the center is also a perception, it's not so easy in a symmetry. You will feel the center is somewhere here, okay. So what you have to see, not this side to this side, you have to see this side should be exactly center inversion should be there. So if you keep doing that, somewhere is the here. So this side you see 2 of them are here, 2 of them are here, and this side 2 of them are here, okay. So you try to see, or if I am wrong you can tell me where could be the center. Here, okay. So this is the one you have to take the B 0 and for the calculation of your G value. So G value when you calculate, this all will go below this. So you know the H, the frequency of the machine also will be given, and these are all constant, you get the G value. So if the frequency changes, G will be slightly this B value will change. So when nu will change, B will also will change, but G value will remain constant. G is a fixed parameter, it will not change. So now you see if I get the field little bit lower, okay, so nu is also going to be little bit lower, okay. So like that it has to, because this has to be constant, okay. So that's how the measurements are. And now you for the copper ion you will hardly get such kind of nice symmetrical signal, because the spin density distribution is not actually spherical, it is rhombic or it is aspherical some of the way. So copper has mostly two kind of intensity like signals, one is for G parallel and G perpendicular. So now what is G parallel? So G parallel is the one which is perpendicular to your applied field, the field. So in this case this is the one or this is the one. G perpendicular is the one which is along the this and along this, so it is the xy plane. So xy plane will call it G perpendicular and the z component I will call G parallel, okay. So the one applied to the magnetic field will go G parallel and this is the G perpendicular. So this component is equivalent to the D component and this component equivalent to E component. So this is axial and this is equatorial. Okay. So now if you have these two parameters, so what happens in copper 2 plus, the signals will be coming. So copper has only one unpaired electron, and if it is nowhere in the free electron, I am supposed to get only one signal. Okay. Now moment I have this electron on the copper center, it has nucleus, it will start coupling with the nucleus, and then it will further split the two lines into more lines. Okay. This will become more lines. So this is electronic energy levels, then they will further couple, they will produce more energy levels here, and then they will be undergoing the transition between them. This is invalid then. So what we have, this initial splitting, this is the final splitting. So I will get the signals because of this, and this is no longer valid. So for the copper, I will not get the signal, I get the signal maybe like this. Okay. So so now this is the component, so this is a G parallel and G perpendicular, so this can come this side, or some of them can come to this side, depends upon the this shape or that shape. So it depends upon the shape, and this is the G parallel component, where this is the separation is equivalent to the coupling constant and due to the parallel. Okay, and this is somewhere it will come here, somewhere it will be like this, it is actually coupling constant due to G perpendicular. Okay. So now depending upon the nature of the bond and distortion, this separation will be changed, they will become closer or become wider, and that is something something is important in the bioinorganic chemistry to deal with and characterize which kind of environment, which kind of metal center. So now a few minutes ago for you EPR spectroscopy was just some numbers and some signal, but now it is speaking about their chemical environment and the distortion. So it gives you a tool where you can look into your system and you can predict about it. Okay. So I have a okay. So now let me just check it here. No, it's okay. I'm just looking. So now too many lines and too many signals will come, you will have to not get a feeling. Okay. So we have given you the basic signal. So now I just explain you another parameter. So now if I have an electron in the free space, I get only one signal. Now I have the same electron on the carbon atom. One carbon atom I take, I put one electron, it becomes carbon dot minus. Now if I take an EPR signal, okay, how they look like? They look like this, and then tiny amount of here two satellites will come. Okay. So why I should get the satellite and also big features? This is the features for this transition. Okay, normal electronic transition, and that is the electron is sitting on the 12C, and their number is nearly 99 per 100. Okay, and this is the features, it is 1 per 100. So this is the one which is due to this difference from here to here is the coupling constant of the electron with the nucleus of the carbon. For carbon 12 we do not see it because there is no nucleus. For the carbon 13 you can see that because this spin active. So then you can measure it. So this one, if the strongly coupling and how much. So if you put a carbon dot minus and methane radical, the coupling constant will be different. Why? Because in carbon atom the electron has to be stay only on carbon, and in the methyl radical the electron still can go towards the hydrogen, and the spin energy in this orbital environment and all are different, and coupling constant will slightly change. So there this also will slightly change. and sometimes they are distinct, not little, a lot maybe. Okay. So this will be telling you about the, so now if I put a benzene ring, okay, I drawn, so there also I will get signal for the proton. So for benzene you have 6 proton, so I get 6 plus 1 7 signal, 2Ni plus 1. If you do for one hydrogen it is half, so I will get the 7 lines due to the all 6 hydrogen. I also supposed to get satellite for the 6 carbon, okay, and then this satellite may be coming in the noise or can be good intensity, it can come. So if the spin density is mostly on carbon, it will get some amount of spin density for the carbon also, but the value will be less because now the same intensity electron density is distributed over 6 carbon. So spin density, this the coupling cost will be smaller. So how much electron density you are putting on each carbon, that matters on their splitting, this signal where they will come, this one. So more electron density mean they will be far, and the small lower intensity mean they will come closer. Sometimes they can fall here also, you are not able to see it, or sometimes they are too noisy and they are not detectable. So if you cool the sample, that time this kind of intensities become stronger and more clearly seen. So you are looking for satellite in your EPR spectroscopy, and they are the characteristic, and then they want to, you have to cool the sample, different temperature. Okay. Now can you switch off these lights on the stage light? Stage light, switch off. Okay. So now EPR spectroscopy you just all drill about the this. So now this is this is the copper EPR. So these are the 4 lines I was talking about because of 3/2 spin, and this is the G parallel and G perpendicular. Okay. And here this is the Gaussian first derivative, all you know, and spin up and down, okay, and you get in EPR whatever the one much smaller, all I spoke, and history, this we spoke, okay, and this is the formula, the one I was writing here, and these are the formula, and here if the B0 comes from the where the transition is going, and this new we are fixing, and other things are all constant, okay. Now if you keep going, so this is the machine where you have the magnetic the field, there is a magnets where they are applying the magnetic field, and then there is a radiation are sent here, the signal for this microwave frequency. This is the microwave frequency box where the microwave is generated, and here is the one, these are the 2 big magnets, okay, and here is your sample which look like this is the sample here, the is gone inside, okay. The signal will come like this, and if first derivative will come like this, okay. Now these are the circuits, and this is the machine where you control the different temperature or other thing will be displayed, okay. How you the signal transfer and all. So now it is a one spin, I said free electron, and then without magnetic field, moment you apply magnetic field, you can have 2 types of rotation, clockwise, anti-clockwise, and then if you apply the vector law, so you can have its vector component the upward or downward, okay. Now so this is the splitting, and you can get the signal like this, and first derivative look like this, and you can calculate G, okay. So you know the nu from the machine and B from your measurement, the field, the way I was calculating, then you get it, okay. Now these are the shapes where I was talking. So you see spherical, all are same, and some cases it is like this or like this or like this, okay. So this is called rhombic, these 2 are called axial, okay, and this is called isotropic, and these are the all thing you can be seen in the EPR spectroscopy. So if it is spherical, the signal will come like this, so much symmetrical, left side and right side from the center both are same. Moment it is become axial, in the GZ is greater, so your signal will be here is a higher and here is a smaller intensity. With reverse way, Z component is smaller and XY is higher, this will be coming to the other side, this will be coming to this side. So perpendicular will become intensity higher and parallel will become smaller. Now if you go to the rhombic case where all components are different, the signal intensity will be coming to all, if you almost this one you bring it here and this will be shift. So if you sum up, this is merging here, so it will come like this. So this is the rhombic, okay. Now Moment you have this different this nuclei and the electrons are there, so the electrons also will couple with the nucleus, and then they will further split this electron energy levels coupled with the nuclear energy levels, and then you further lines are coming, what I was talking. Okay, now the transition will start between them. Okay, applying the this your selection rule. Okay, so now you the signal, instead of one signal, when you are getting two, the transition can between these two or these two, you get these two signals. So now what are the points? If I have the same amount of spin of the nucleus and the electron, but gyrometric ratio of the nucleus is different, then their coupling constant also will be different. For example, nitrogen and phosphorus both are in the same group of the periodic table, but if you keep one electron on nitrogen, one electron on the phosphorus, and for phosphorus it is nearly 3 to 4 times higher coupling than the nitrogen. Why? Because gyrometric ratio of the nucleus is higher. So now what is the gyrometric ratio? So now if this is the nucleus, it is spinning and also it is rotating, it is like earth, right? So now when you apply magnetic field, you forget about the nucleus. Moment you apply magnetic field, how fast it spins, this is the one, it is the gyrometric ratio G. The lambda vector is the with respect to the axis of the electron, how fast it is spinning, that is the measurement of the G value. So if G is high, that means it is spinning around its own nucleus, forget about the nucleus of the this protons and all, its electrons own axis, as around its own axis. This is its own axis, how fast it spins, that is the G. Okay, so this is the physical meaning of the G, and then these are the all nucleus, you can see how much they have spin and difference. So I told you in proton, a carbon, you have only nearly 1% of the 13C, so that's why I gave you these values 99, 100 and all, why satellites are coming. Okay, and then you see for the copper ions, so if I have no coupling with anyone, I get one signal for free electron. If I keep one electron on the oxygen or sulfur, okay, it will be just one signal because it has 100% spin free nucleus. Okay, but moment I put the same electrons on the suppose on the any other where you have the spin activity like phosphorus, okay, it will become, it is spin equal to half, or fluorine, okay, half. So F dot or P3 just phosphorus atom, they will produce two signals. Okay, and these signals will be like double 2 times, because 2 n equal to 1, if you do I equal to half, and then it will come like this. But for fluorine, coupling constant will be different, and then the phosphorus. So if you put F dot and phosphorus atom separately, you can keep it in a chemical condition and you can make EPR, you will see their signal will be coming same, but their splitting will be different because their gyrometric ratio is different. Okay. No, okay. So now if you go to the one where you have for nitrogen in the like phosphorus, but it has spin equal to 1, not half. So it will get 3 lines because -1, 0, +1, and then between them all possible transition. Okay. Now if you go to I equal to 3/2 like copper, you get 4 signal. Now if you get 2 nucleus which I equal to half, so then you will get 3, because 2 of them will be merging here in the middle, you see here. Okay, so that's why it has become double intensity, they are here. So this is the how it is coming. So if you take 3 of them, so 2 of them will be further, 2 of them will merge here, so they become double intensity, they will be smaller, like Pascal law. Okay, so if you keep somehow them separately, it will be different, you will see instead of getting triplet you get doublet or doublet, this will become 2 times, or this will triplet will become 2 times. Okay, but when they merge it, so middle intensities are increasing, they come in the same place. Okay, so these are all number of counting, so 4 nuclei will give like this. So this is the copper perchlorate and how it is coming, you see here. Okay, and these separations are something to do with this called G parallel and G perpendicular, and this separation is called coupling constant due to the G a coupling constant with the copper nuclei, you have to call them A and parallel sign. So A parallel and A perpendicular are different quantity, and their values have something to do with their chemical environment, distortion, geometries and all. Okay, fine. So now these are the things I spoke a bit. Now if you can have a software called easy spin, okay, and you need a MATLAB, and if you both you together work with, and there are codes where you can write what are the codes you are like you put it here, spin, G, nucleus, this, that, and all together, and if you have a methyl radical, you can produce the signal, 4 signals, you know. Now you can put a coupling constant, if you change it, you can make it a give higher value, they will become wider, they have a smaller value, they come closer, and then you can signal intensity, this is the width, you can change by putting their Lorentzian and Gaussian parameters. If you increase the values, they will become wider. Okay, so all kind of shapes and all what you come from your experiment, you can play with your the software, you can fit it. Okay, and say which is due to the Lorentzian, which is the Gaussian, and which is due to the coupling, how much is the coupling constant. So the coupling constant here to here and here to here or here to here all will be same if they are perfectly symmetrical. If they are slightly distorted, this side will be slightly different than this side, tiny difference will be there. So that means what? It sense like if ant is touching me or snake is touching me, the way they touch, one will bite you, different pain, right? So you can sense it. So EPR spectroscopy is so sensitive about its symmetry, geometry, and spin distribution. Okay. Now this is the copper 2 plus ion, and you can see the G perpendicular is lower than the G parallel, and this is the one from the software you can just bring now you can start simulating. Here is the one where the cobalt has 7/2 nuclear spin and 1 unpredictable will couple, and we get 8 lines are coming here. Okay, and there also this is a distorted geometry, and tetrahedral is not perfectly tetrahedral. So that's why it has Gx, Gy, and Gz components are different. You see the values 2 point something, they are not same, and then their nucleus couplings, so 8 lines are coming here, and these values are also given here around 21 and 30 actually. What is that? Their coupling constant. So now we had a very so for some of you it is just number of lines but it is just not number of lines, it is the start with the how many lines. It's like hospital, how many patients are entering the door, okay, inside the door, after that how many problems they are bringing. So now you can see the problems here, you can diagnose and then talk about them. Okay, now this is a similar one, a compound, but it's pentacoordinate and the 2 radicals are coming, but you get these signals due to the these electrons are close to more here, earlier case it was more close to the cobalt, here is more close to the nitrogen, and these signals are mostly to the nitrogen coupling, and 2 Ni plus you do, it's a 6 signals. Okay, and some moments are coming due to the this manganese. Okay, and the same signal compound when you cool it, this part where you had this becomes broad, and this is the part where is a forbidden transition came. It has spin more than half, it has equal to maybe 2 or 3 something, so its corresponding transition due to delta m is equal to plus minus 2, this is the transition is coming here. Okay, this is taken at 77 Kelvin. Okay, you see the temperature, earlier one as the room temperature. Okay, so it's a half spin system or more than one spin system, we can also prove from the EPR spectroscopy. Okay, these are our molecules, we synthesize them, we make crystals, we characterize them by X-ray structure, then we make their EPR. Okay, and this chemistry is not so easy. Okay, and then here you can see iron, so this is a signal due to this nitrogen, the middle here 6 signal, and these are the signals are due to the iron, and the distance the difference between them is the coupling constant of the electron with iron. Okay, so again the another the same compound at the 77 Kelvin, so the coupling constant is very strong, you can see it is 250 megahertz, earlier uh, it was here around, how much was for iron was 744, here it comes about 740. Okay, so slightly change in the values, and this is for the one signal for electron on the here and another signal for the iron, we can get for both. Okay, so it is keep on going. Okay, and sometimes they will give the coupling for the chlorine also. So now this is a cluster, so we got is like if you for S4, but here is a chlorine bridge, okay, it's like Cuban type, and you have the further radicals, two here radicals here, two are non-radical, and there are two of them iron 3 plus, two of them are iron 2 plus. So this is a signal. If you see for the this electron is coupling with this nitrogen, 6 lines, and this is the signals are due to the no sorry, this is the signal is due to the and this is the signal are due to the iron, okay. So iron signal also we got, and the values actually 2939. You can see these values are nearly 5, so very small here, and this is how many times, 50 times, and so they are far. And you can see with respect to the center, they are not symmetrical. So these environments are 5 coordinate, and they are not perfectly 5 coordinate, and you get, so you can sense the environment, and from the separation you see this is not very symmetrical, it is little close, it is far, okay. And here the nitrogen couplings are hiding, and these are the coupling to the iron. Iron is not 100%, it has small percentage of the iron spin active nucleus. So signals are coming due to the electron, and then also electron coupling with the nucleus. If nucleus spins spin active nucleus of metals are high, then their intensity will be high. If they are low, they will be coming very low, okay. So in this case some amount of impurity also coming, that also you can locate, okay. So now this is a copper compound, octahedral radical, okay. So here with the coupling with this, you see coupling cost of the cobalt is 22, and the nitrogen coupling is seen, where is it or not seen, coupling is seen around 2 megahertz, okay. So electron, this coupling, this EPR is coming, these 8 lines here are due to the cobalt, these are the lines, and the some lines here in this band here and due to the nitrogen coupling, okay. So you can keep doing this. This is the mercury, okay. Here these are all compounds, so I think we don't need to speak all. Now here you see zinc is having a very small amount of spin active nucleus, very small percent, and the EPR signal is usually electrons coupling, and these two electrons are coupling. So when we measure the magnetic property, this molecule has two types of state. One case this both are parallel, another one is up, another down. So when we do magnetic measurement, we found it for this one we supposed to get the magnetic momentum whatever it is half coming. So it is having two type of spin state, one is singlet, another is triplet. So we get the EPR signal for the triplet, and this triplet species coupling constant are coming there, and also this compound is giving NMR signal which is for the singlet species. And how do we know that it's half of the singlet triplet? We calculate the energies between the singlet triplet is very small. When it's very small, that means both the species are possibility populate in both the states, Boltzmann distribution. And when you did the magnetic measurement, it value exactly came half, then it's supposed to come for the 2 electrons. That means if you take 2 of the molecules, one is singlet, another is triplet. So singlet will give no EPR and no magnetic momentum, triplet will give the magnetic momentum, that's all. So now Boltzmann distribution, EPR spectroscopy, magnetic measurement, all you prove, you speak. If you just speak about the NMR or the EPR, you do not know how much fractions are populated, okay. And here in this case we so you can see here these two compound how they are different. So these 6 lines are here, and these are the one is coming to the iron nucleus. In the zinc it is not coming because its percent is very low. In iron is significantly higher spin active nucleus, okay. And also iron has own spin, so its own spin also with the nucleus they are all coupling, and then you get their signal also here. This is the for the iron, this is the nitrogen. So EPR spectroscopy speaks about many more features, okay. Something I think we got to, he didn't put it here, okay. Okay, fine. So I think we have covered a good amount of feature. So you can now ask me any questions you have. So next 1 hour you have seen, right? As I said. Okay. So now my question is that 8 classes are the similar classes or very different classes? Yeah, so very different. So same thing, you look at those 8 classes in my 1-2 hours lectures, they are very different. I take our the very fundamentals and to our own molecules, okay, and how EPR spectroscopy we can actually bring. And then if you have a nickel to 1 plus, it is like a D9 system, it will have given the similar EPR like copper 2 plus, because they are D9 system and their enter distortion and all be similar, and then they give you same similar EPR. Okay. Now how are coupling to the nucleus? So in the biological system, copper is lot connected to the histidine. So histidine has a nitrogen and is a pi star orbital. So electron density from the copper also partly goes to the histidine side, and then they start showing the coupling due to the nitrogen also. So all these lines will be coming and they will further split due to the nitrogen. So 4 lines and then one big lines you see. Now every line will be start splitting due to the nitrogen also. Okay, it is the filling. If you have a wound and you put a bit of salt on it, you see the filling. So EPR is like that. So one effect you can put other and you will feel it. Then if you put a little bit chili powder, further you see. So that is what the EPR spectroscopy, they add on each other, because they further split the energy orbitals and then they start undergoing the transition between them and them. So you have much more number of lines and their features will come. Now they are symmetrical, unsymmetrical, shape, based on that all different shapes will come, and you can play with them in the software, you can simulate them and you can speak about them, who are who, which one, how much, what exactly you can quantify. Okay.
SwayamPrabha, Digital India, Educated India.